Okay, so let's just recall what we want to do. That is actually want to calculate the free energy for the weakly interacting electron gas. So I just wrote down again free energy. So recall that in the limit t to 0, this gives us a ground state energy. And this is just recalling the action of the weakly interacting electron gas, which we will now do. And the idea is to calculate the free energy in some perturbative expansion, and what we'll still need to have is the link cluster theorem for the free energy. But then let me just also recall that we already made some very qualitative considerations which led us to the assumption that, or the expectation, that there is a parameter that controls the weakly interacting regime. So if we are at weak interactions, there should be some parameter appearing as we go to higher and higher order that controls the expansion, the asymptotic expansion, and this was obtained from a ratio of the interaction energy and the kinetic energy. We said, well, that if we are in the high density limit, we should be safe. So the parameter that should appear is related to the density. So let me just recall the estimate. We said that the ratio of these two energies can be compared to the radius of an average of the volume an electron occupies on average, that we called R0. This is related, of course, to the density. So this radius can be estimated as one of the density to the 1/3. Okay, that's the radius. And then we had the Bohr radius, which is h bar squared over mv squared. So if you put in this and neglect numbers and factors pi and whatever, the parameter that should be appearing is given here. Okay, and this is like in the high density limit, the Fermi momentum was large, and then this should be small. So just to recall this. Now this is the goal, so let's just start with the first thing that is actually trivial, which you already considered, which is the partition function of the non-interacting electron gas. Well, we have just already, before making this qualitative estimate, we are already like based on like filling the Fermi surface, we already looked at the ground state energy of the non-interacting electron gas, but just to see how this we would get from the field integral formalism. Okay, so just recall that the zeroth order is, and let's call this zeroth order just F0. So that's the free energy of the non-interacting electron gas, and this is given by log of the partition function of the non-interacting electron gas. So if we take the non-interacting gas, this interaction potential is 0, so that's setting the electron charge, let's say, to 0. We have a field integral over a quadratic theory, which is diagonalized by the form momentum and the spin. So if we now do the integral here, this will separate into a product of integrals over psi pi. So this will be a big product over 4 momentum pi. And for every 4 momentum pi, we have just to do a Gaussian integral, which gives us the determinant. So which gives us just the term here. And then if we take into account the one comment that was made on the normalization factor for Matsubara frequency representation, recalling that these fields carry the dimension of an energy, then that's still some factor better. Just fight first this. So the partition function for the free particle just separates into a product of 4 momentum. So this again separates into the product of Matsubara frequencies and then 3-dimensional momentum. And there is a better appearing here, which was the comment that we had before on the normalization of the Gaussian integral for Matsubaras, and then we just get here, well, the determinant of the product of the eigenvalues. This is here, and then we should recall, well, that we also have a sum of a spin. So this will lead here also to a product of a spin up and spin down, but they give the same. So this will just appear with the square. Okay? No, this is the just the partition function, then the free energy will be just minus 2t. Then we have here a sum over Matsubaras, epsilon n, or actually I call them once epsilon n and sometimes omega n. I should call them that's omega n. Omega n. And then sum over 3 momenta, and p is log minus omega n plus p squared over 2n. Okay, so this is what we get for the free energy of the non-intacting electron gas. We still have to talk about these sums here, but this will be later. But actually we already calculated this result in a simple way, of course. I mean, can be done much simpler, but just to see once how the function integral formalism works. Okay, so this is just using the basic property of Gaussian integrals. Okay? Now, what we then want to do is actually we want to now consider first, second, third, and so on the order. And what we need to organize this expansion is we should know how to do a perturbative expansion for the log. Okay? So before we consider perturbative expansion of endpoint correlation functions, now we have the log of z, and we want to do a perturbative expansion of the log. Okay? So again, if you do here perturbative expansion of the log, what you can do is you can first expand the z in the interaction in some asymptotic series, but then still expand the log. Okay? So that's the same as we had before in the correlation functions, where we said, well, we should do an expansion of the numerator and the denominator. Again, there's two expansions, first of d and then of the log. And again, there's something very nice, which is the link cluster theorem. Now not for the correlation functions, but it's for the free energy. And then we just state it and then comment on the proof. So the linked cluster theorem for the free energy is stated as follows. First the formulas. So this formula states that to find the free energy in a perturbative expansion, we can keep the zeros order, and then what we should add is just the perturbative expansion of the partition function would give these terms, no? Okay? So what we have to do is to do the perturbative expansion of the partition function, only keep the connected diagrams. Okay? So the free energy, and again this is due to some cancellation of two expansions of the log and of the partition function. So the free energy is obtained by expanding the partition function and not the log of the partition function. Okay, so this of course simplifies a lot, and then keeping only the connected diagrams. Okay, so here we don't have any external like legs which would talk about like vacuum, non-vacuum diagrams, so only keeping the connected diagrams. So this again will be a great simplification for our calculation, because now we know what we have to do if we want to go to higher order. So that's the F0 that we calculated here. So F0 is zeroth order. So now if we want to calculate the higher orders, well, we just have to expand the partition function in the higher orders and draw all the connected diagrams, then translate them into formulas and see what this gives. Okay? Let me just give some So just, I mean, if you want to keep this like the message in some compact form, you can say that dropping disconnected contributions is equivalent to taking the log. Okay? So start off from quantitative expansion of the partition function. If you only keep the connected diagrams, this is equivalent to taking the log. Okay? Now, one can prove this again, like looking at combinatorics, but there's a nicer proof, much more elegant, which uses the so-called replica trick. So, which uses that you can express a log of a number as some limit where you sense. Okay. You can use some clever representation of the log, and then this allows you to show this min cluster theorem in a very simple way. So either we are going to make this in an exercise, or I just comment on this on another lecture, but let's just now proceed. So we will still come to the proof, and I think there's, like when we come to the proof, there's some nice that we can introduce, which is a so-called replica trick, which is very much used when you discuss disordered systems, and it's good to know it, and you see that this is a very nice, elegant way to prove the min cluster theory. Okay, so now we have the prescription, and now let's come to the really, more interesting thing, and start looking at the interaction contributions to the free energies. So the non-interacting part is given by this. Still have to talk about the sum, but let's first look at the first order. So F1, following this prescription, is given by just taking T to the L cube, then sum over sigma prime, sum over P prime Q prime. So this is, we said we represent by something like this. So now what we have to do is we have to draw all the connected diagrams and translate them back again into analytical expressions. Well, if you just have one interaction vertex, of course all diagrams are just connected. So in diagrams, what we find, I put here the equal, knowing that all the rules, like we have to translate this back into formulas and blah, blah, blah. But like this equal, we know how to understand. So now what we find is that the first order interaction correction to the free energy is given by these two diagrams. Okay? So let's discuss these two diagrams, what they mean and what they do. And this okay, so let's follow the rules. Let's translate these diagrams back. Let's start with this diagram. This has a long name. It's called the Hartree contribution. Okay, so the first thing that we do is we want to translate this back. The first thing that we do is we should put back labels onto this. Okay, so this is a closed propagation line. So of course we consider this a momentum space. So we have some form momentum p and some spin index sigma. Okay, that runs around here. Then we have some p prime and sigma prime. And we see that actually this line here has q equals 0. Okay? So this q equals 0 just has to be because, I mean, this light closes into itself. Okay? But now we already see what this gives. Well, we always said that we have like the freely moving electrons which are interacting among each other, but we shouldn't forget the positive background of the ions, which lead to overall charge neutrality. And overall charge neutrality was guaranteed by saying that the zeroth momentum contribution of the potential should be 0. So this diagram is just proportional to here. So this is itself 0. So the Hartree contribution is actually 0, and the reason for this is just the charge neutrality. And can make this more clear by looking if we want to translate this back into an analytic expression, okay? Just one of these bubbles here, this fermion groups. So this would be a 4 momentum, which we can write as a momentum over epsilon and momentum over 3 momentum p. The sum over spin just gives a factor of 2 because, I mean, and then we have here the let's write it like this, the non-interacting Green's functions. Okay. Again, we encounter here some sum over Matsubara's, which we still have to do, but this is something we will learn next week. Like, that's the last detour for the moment that we'll do. But once you know how to do this, you know actually how to do the sum, and you will see that this here is proportional just to the number of electrons. So if you do the Matsubara, this gives you like the distribution, Fermi distribution. So at t equals 0, whatever you're interested in, this just gives it a total number. So what this Hartree diagram describes is just the classical interaction of charge densities with the Coulomb potential. Describes classical interaction of charge densities the Coulomb interaction. Okay, in a set, so the reason why this is 0 is that the electronic density cancels against positive, cancels against the background, that was, I mean, what you always said, charge neutrality. Okay. So this gives 0 now. Just one brief comment. So this is actually all considered on this idea that you have a uniform electron gas moving on this positive background. Now, if you're considering, for example, a disordered system, then everything gets much more complicated, and actually the Hartree contribution will give a finite. This is one case. Now, okay, so that was the first. Now let's look at the second diagram here and see if there is something interesting happens. This is the second diagram, which also has no name, which is a Cont contribution. So let's do first again what we did in the other diagram. Let's assign labels to it. So we have some momentum, for momentum passing here and some spin. Now the momentum here can be changed due to interaction, like due to emission of a photon, which carries some magnetic field. So it can change to T plus Q epsilon plus omega m. That's the same spin. Okay? And then, well, here, because of all momentum conservation, we go back. Okay? Now, what this actually describes is, so we said that this is like the classical contribution. Okay, so what you consider here is this bubble here corresponds to density. So this is what I wrote here. So this is the interaction between densities. Now this, in a way, if you start from this diagram, you have here the densities, and just pairing this gives the classical contribution. Now we know that we have here, like considering quantum mechanics, and we have indistinguishable particles. So there's always the exchange contribution, where, well, say here the electron this electron scatters from this this electron scatters from this electron. This would be the diagram, but there's always the exchange contribution because of I mean, it's indistinguishability of particles. And so if we, instead of saying that like the electron scattering is just given by this, but we take the exchange process, we get to connect this and this and this and this, and this leads to this diagram. So this is describes some quantum contribution due to the fact that we are considering indistinguishable particles. So this is of quantum mechanical nature. And actually, if we now want to translate this back into formulas, we see that we have one fermion loop. So one fermion loop means we get a minus sign. So what this wants to do is it diminishes the energy. Okay? It's negative. And actually the physics also is then clear, because we said this has to do with the indistinguishability of particles. Okay? So this is like a quantum contribution. Now this means that the particles we are considering here actually are those obeying Fermi statistics. Okay? So if we have fermions, then and we have fermion statistic, well, this means that these particles do not like to come close to each other. Okay? Because of Fermi statistic and Pauli support. So there is, due to statistics, they try to avoid each other. Now this means that they don't come too close to each other, like as if they were distinguishable classical particles, and this means that there is some quantum correction to the energy just due to, I mean, the, let's say, you know, because of Fermi statistics. Yeah. Let's see. So the electrons, which are of course fermions, tend to avoid each other more than classical particles would. And this means that the quantum statistics lower the correlation energy below what you would classically expect, and which was 0 in here because of charge neutrality. Now, who wants to explore this a little bit more? I just give you like one thing that you might want to look at. So, if you want, to explore this a little bit more, you might consider just a point-like interaction. So let's say point-like interaction between electrons. Yeah, so no V of Q, just point-like interaction, then of spinless electrons. And there you should actually see that there's two contributions always to the interaction. So there's a Hardy contribution, the Fock contribution. And you should see, well, just if you think about it, so electrons that just can act on the same point, they are spinless, but because of Fermi statistics, I mean, this will never happen. So you should see that the Hardy and the Fock contributions cancel each other for point-like interactions of spinless electrons. Okay, so just there you can see like this. Just as an exercise if you want. Okay, so this is like we understand kind of what this diagram describes. So let's translate it back into formulas. So we get the minus, as already said, because of the Fermi loop. So the overall factor, okay, I didn't write it down, but the factor was T over 2L cubed. Now the factor 2 comes from summing over the two spins. So we have 1 free sum over spins, spin up, spin down. And then we have a sum over P, a sum over P plus Q. Let's just write it different. Let's write it as sum over P and P prime, because this is more simple. So it's just the same. I mean, use P prime and epsilon n prime. Make it more symmetric, and then this will be P minus P prime. So we get here a free Green's function with 4 momentum P, a free Green's function with 4 momentum P prime. So G0 P, G0 P prime, and then we get the interaction potential at P minus P prime. Okay, so this is what we find from first order perturbation theory. Now, this is a 4 sum, so this is a sum over Matsubara frequencies and 3 momenta. So what we find always in this expression, we already found in the 0th order, while we had the sum over 4 momentum. Now this 4 momentum always includes the sum over Matsubara frequencies. We have to know how to do the sum over Matsubara frequencies. This is like what we will discuss next lecture, how to do summations over Matsubara frequencies in some efficient way. So here I already like anticipate what you would get there. So we will verify this later or in the next exercise, or let's see. Once we know how to do the Matsubara frequency summation, you can show that this then, after summing epsilon n and epsilon prime, this is again actually as already said here, so this is proportional to the number of electrons because the Matsubara of a Green's function just gives you the distribution. And then at 0 temperature, well, P just gives the number. So again, just say here, well, this is then the Fermi distribution of epsilon P and the Fermi distribution of epsilon P prime. And here the interaction is P prime. Okay? So this is all based on the statement that this here gives the Fermi distribution, which we'll prove later. And so this next lesson, or this lecture, then if we now go to the 0 temperature limit, the Fermi distribution just becomes step function. So what we sum up is here all momentum up to the Fermi momentum. So what we end up with 1 over L to the Q. Then we have P and P prime, both absolute small value smaller than P Fermi, which is square root of 2m chemical potential. And what we sum is the interaction potential, which is given by this. Okay? P prime smaller than 2m, which is the terminal. Now, again, I mean, this is an integral that one can do exactly. Maybe an exercise you have to see, or if you want, this is also in textbooks, you have to see if you make an exercise. But what you should do is to convince you like how this contribution scales. Okay, so just in the physical parameters. And so for getting factors 2 and pi and whatever, one can show that this scales with minus e squared L to the cube P Fermi to the power 4. Okay, so this is something you just may want to convince yourself. So converting the sums into integrals will give you power L to the 6th, and then you have like just to count like how many powers you have in P, and they are all cut off by the Fermi momentum. So this is just power counting. Okay, this you can convince yourself. If you want, you can be more ambitious and see that there will be some factor 1 over 2 pi to the power 4. Okay, but this is just the result, and this is now allowing us the following. So if you recall what we had found for the free energy of the non-interacting electron gas, which we calculated in the very beginning, and expressed this now in units of the natural energy that appears, the Rydberg energy. Over m squared over. Then you find that what you found there, but still, this we have calculated in the very beginning, just using like filling up the Fermi sea. To do it in the path integral, we still need to do the Fermi summation and so on. But just you can confirm this, that in natural unit, this contribution scales as n, particle number, divided by the small parameter Rs squared. Okay? Now, if you translate this here into a dimensional quantity, which you express in terms of the particle number and the dimensional parameter, you will find that this actually, so you can verify this, scales as 1 over Rs. Okay? So this is already like confirming then our very qualitative analysis that we had at the beginning, namely that we have in the large density limit, we have this dimensional parameter Rs, much smaller than 1. And if we do the perturbative expansion, we already see that in first order perturbation theory, we get an expression which is smaller in Rs compared to the nearest one. Okay? And this is like what you can just confirm from this. So what we still need to do next lecture is to discuss how to convert, how to do Max-Bar summations. Now once we do this, we can then actually go to the higher orders. Okay, so this is like one more technical interlude that we do. Max-Bar summations, and then we will go to the higher orders, look at the second order, and there we should already see like what is going on. And just to give you an outlook, so what we said today is, well, all these perturbative expansions in the interaction actually have to be careful because they're like asymptotic expansions. Now, what we did is so far just calculated the ground state energy in the first contribution. Now, when we come to the second order, there will be more diagrams appearing, but we can identify, again, interpreted like physical, giving physical content to the diagrams. We can identify a certain kind of diagram that will be dominant in the large density limit. And this is very nice because this then will already hint us like how to go to higher and higher orders. We can see that in every order perturbation theory, there's a certain class of diagrams that dominate in the physical parameter which is given by the density. So in the large density limit, there's in every order perturbation field, there's a certain class of diagrams which give the dominant contribution. And this then will allow us to do some infinite series in perturbation theory, which, like you say, oh, we said infinite series doesn't make sense. No, there's one way out. This is if you would take all diagrams in every order, it's just exponentially blowing up the combinatorial factor. But what we can see is that there are certain classes of diagrams which are more relevant than others. If we stick to this class of diagrams, we keep in every order the leading term, and we beat also the combinatorial factor, because then the combinatorial gets smaller. So we can do some infinite series of certain classes of diagrams, and this will then be done later on. And then, so this is the outlook, like first some technical, then second order, then infinite order. And once we have identified like the specific class of diagrams, we can connect this to some other method which is deriving effective theories. So once we have identified a certain class of diagrams, we know kind of what are the low energy degrees of freedom that are relevant. And this will allow us a different approach, contrary to perturbation theory, which is built on Hubbard-Satonovich transformation, which will just stick to this physical channel, giving rise to this certain class of diagrams, and we will derive an effective theory for this. Okay, so this will be like the next 6 or whatever lectures. And then we will do the same program for other problems. Okay.